chapter 17, slides 4 through 7. We're now going to determine if a ring is aromatic or not. Okay, so we're going to do this, as we always do in organic in this course, we're going to do it qualitatively, not quantitatively. If you're interested in this quantitatively, you can take a physical organic course and study orbital theory, but we're going to do it in a very simple way using Huckle's rules. Now, there are 3 labels we can give a ring. We can either say the ring is aromatic, and this is when we get our super stable situation, right? That's what we've been talking about, this aromatic ring. That's what I want to know how to be able to identify, because it has these very stable properties. If it's not aromatic, it has the potential of being anti-aromatic, shown here in red, or non-aromatic. Okay, now it's important to understand that if we figure that the ring is anti-aromatic, it is not very stable at all. In fact, it's worse off than being conjugated. It has added instability to it. Non-aromatic just means it may be conjugated, but it doesn't have any extra stability that the aromaticity shows, right? It's just a typical conjugated system like we saw in previous chapters, right? There's a little bit of extra stability, but not the aromatic extra stability. So let's take a look at a few systems and how Huckle's rules help us to qualitatively assess whether or not a ring can be considered aromatic, anti-aromatic, or non-aromatic. The first rule that you're going to ask yourself is this. Okay, so we're going to start with the first question. You look at the molecule and you ask yourself, does it have a ring? Right? In order for aromaticity to occur, you have to have at least one ring in the system. Okay, so you ask yourself, is it a ring? Let's look at benzene as an example. We already know benzene is aromatic, so let's go through Huckle's rules, knowing that benzene is already aromatic, and see how they apply. So using benzene, so we're going to do Huckle's rules for benzene. Is benzene a ring? Yes. Check. All right, we're good. Let's move on. Step 2, do the p orbitals of the ring overlap in conjugation? The ring must be planar to do that, and I've drawn the diagram for you in previous slides. Each one of the carbons is sp2 hybridized, and it appears that all of the p orbitals are in alignment, they're conjugated, therefore they have to be planar, otherwise if they were not planar, we would have that YZ orientation problem where the pi orbitals are orthogonal to one another, but they all seem to be aligned and parallel. So this seems to work fine. You have to have full conjugation around the ring. Okay, so if you had one carbon that was tetrahedral, or 2 in this case, so look at this molecule. This diene is a ring, so it passes the first rule, but the second rule states that all the p orbitals have to be overlapping in full conjugation around the ring. Well, you have p orbitals here and you have p orbitals here, but the ones on the end are both sp3 carbons, and there's no full conjugation around this ring. Therefore, it fails number 2. The p orbitals do not fully overlap around the ring. So this molecule is not fully planar, therefore, this cannot be aromatic. It's non-aromatic. So if you fail question 1 or question 2, so if you answered no to either or both, question 1 and question 2, then you're going to assign the molecule as non-aromatic. So for the molecule I just drew down here, this one failed. It was a ring, but because it had sp3 carbons and not full p orbital conjugation, it failed the second p orbital rule. Therefore, it is non-aromatic. Benzene, on the other hand, passes both. It's a ring, and it has full p orbital conjugation around that ring. So we've passed both. So once we get past 1 and 2, we then enter Huckle's third rule. You count the number of pi electrons that are in play, the ones that are in pi conjugation. So if you look, if I just count the pi electrons, there are 6. 2, 4, and 6 pi electrons. So what I'm going to do with this 6 is I'm going to set it equal to 4n plus 2, or I'm going to set it equal to 4n equals 6. So what I've done is I've taken the 6 pi electrons and I've set it equal to the 4n plus 2 and the 4n. What you want to do is you want to solve the equation for n. If n is an integer, 0, 1, right? 0 is an integer, 1, 2, and so on, then it meets that rule. And if it works under the 4n plus 2 rule, it's aromatic. It's only going to work under one of these. You're always going to have an even set of numbers. So that's another thing. You're never going to be working with an odd number. So it's always going to work for one of these. If the integer, though, is only when you set it equal to 4n, then it is considered anti-aromatic. So we already know benzene is aromatic, so I'm going to focus on the 4n plus 2. It's probably going to work here. So you solve for this equation, right? Minus 2 on this side, minus 2 on that side. I get 4. 4n equals 4, n equals 1. It works, integer. Therefore, since it worked under the 4n plus 2 rule, I know that this is an aromatic molecule. Now, I want to show you what this means using a frost diagram. This is another way to visualize aromaticity using energy orbitals, okay? So remember when we did MO theory using Diels-Alder, we did the HOMO and the LUMO, and we mapped out the p orbitals from low to high? Well, you can do this using a frost diagram. Frost diagrams take the ring, and what you do is you orient the ring such that it has one of its points straight down, okay? So one of those points straight down. And then what you do is you pretend to draw a circle around it, touching each one of the angles. So if I were to draw a ring, touching each one of the angles, you would see that each one is in the orbitals, like these are equal to each other. This one's higher and this one's lower. So you actually, it beautifully maps out the relative energies of the p orbitals for that aromatic ring. Then what you do is you take those 6 electrons that are in conjugation and you start filling, okay? 1, 2, because that's one energy. We fill the degenerate orbitals, 3, 4, and then go back on themselves, 5, and 6. What you'll notice is that the HOMO of this benzene ring is completely filled. This is very stable, all right? And so Huckle's rules allow us this little quick and easy cheat without having to do these frost diagrams for every single system. But I wanted to show you 2 ways of doing it in order to understand how to figure out whether or not these electrons in conjugation fit an aromatic system or an anti-aromatic system. Let's take a look at another example. Let's look at cyclobutadiene. Now, let's use Huckle's rules to determine whether it's aromatic, non-aromatic, or anti-aromatic. Is it a ring? Is cyclobutadiene a ring? Yes, it's a ring, so it passes the first test. Number 2, do the p orbitals of the ring overlap in conjugation? Well, let me draw the four-membered ring. We've got a double bond and another double bond, and they all look to, be aligned with one another. So yeah, the p orbitals seem to overlap, and I'm able to draw it so that all of the sp2 carbons are aligned with one another with their p orbitals. So we're good. Check. All right, so now we're going to do number 3. How many p orbitals, how many pi electrons are in conjugation? Pi electrons in conjugation is 4. All right, so which is it going to fit into? 4n plus 2 equals 4. If it fits this, then I know that I am aromatic. Right, so my pi electrons in conjugation, you don't count all pi electrons in the system, you only count the ones in the ring that are in conjugation, and that's 4. So I try to solve for n. Let's see, minus 2, so 4n equals 2. This is not looking good. So now I go 4n equals 4. I try the other rule. In this case, 4n equals 4, n equals 1. This fits. So unfortunately, this is anti-aromatic. Cyclobutadiene is anti-aromatic. And I could use Huckle's rules to figure this out. You could also use a Frost diagram. And what's nice about the Frost diagram is I'm going to show you why this is an unstable molecule. Right? When we did the Frost diagram for benzene, notice that we filled really nicely all orbitals. For this molecule, we reorient the ring so that one of its angles is pointed straight down. And you can see that when you draw the circle around it, you're going to get 2 degenerate orbitals and a high and a low. We had 4 electrons in those p orbitals to work with, so let's start filling. 1 electron, 2 electron, 3, 4. You'll notice that in this anti-aromatic system, the reason it is not as stable as an aromatic system is because you have 2 unpaired electrons in the ring. And so this lends to added instability for the system. What you'll recognize is that anti-aromatic systems have unpaired electrons in their degenerate orbitals, while aromatic systems have filled orbitals. These equations that we write out, the 4n and 4n plus 2 rule, are just quicker ways of determining the energy levels and the electrons in them. It's kind of like a quick cheat. Let's do some practice. I'm going to use Huckle's rules because I find them a little easier to use. So let's take a look at this 7-membered ring. And we ask ourselves, is it a ring? Why, yes, it is. Is it in full conjugation? Remember our conjugation chapter, that carbocation, right? If you had a double bond with a carbocation next door at the allylic position, it was said to be conjugated. So you do have an empty p orbital here. It's just empty. It doesn't have electrons to it. But it is indeed an empty p orbital that can fully share and help transport through conjugation and resonance the electrons around and around and around. So we're good. Yes, it is a fully conjugated flat ring. All right. So I passed steps 1 and 2. Step 3, how many pi electrons are in conjugation? Well, there's 2 here, 2 here, and 2 here. Remember, the p orbital is empty. It just is a doorway through which conjugation is allowed for the electrons to go round and round and round. So the answer is 6 electrons. This works for the 4n plus 2 rule. We saw that for benzene. Therefore, This is an aromatic ring. Let's try the next one. Is it a ring? Yes, it is. Is it fully conjugated in a flat ring system? Well, let me see here. Sometimes I like to just draw it out, draw the sigma framework out, and then represent the p orbitals or the pi bond as p orbitals. And then at this, you have a negative charge. What's a negative charge? Well, a negative charge is a lone pair, and it's in a p orbital. Remember way back when we had amides, and we would ask you what the hybridization for that nitrogen was. Remember that? And I'd say, oh, hybridization has a trick, because if resonance is occurring, it rehybridizes itself so that it can resonate. Otherwise, if it doesn't rehybridize, it won't be able to resonate as an sp3 atom. So even though that atom has 4 as in its stagnant state, the way I draw it, even though that nitrogen atom has 4 electron clouds, you could have jumped the gun and said, oh, it's sp3. But remember, you always had to look to see if there was a lone pair as one of the electron clouds. You had to see if that lone pair could play a role in resonance. And if it can, you had to drop its hybridization, because it will rehybridize in order to play the resonance game. That is a stabilizing force. So we have a lone pair here and it's in an allylic position, just like the nitrogen is, right? The nitrogen is right next to a pi system, just like this double bond is next to the lone pair. There's resonance going on here. So therefore, round and round and round, how many pi electrons do we have in step 3? Pi electrons? Well, you have the 2 of the pi bond, 2 of the other pi bond, and then you have the lone pair. So that's 6 electrons. And we know 6 electrons fits into the 4n plus 2 rule. Therefore, because n equals 1, we can solve for it. It's aromatic. Great. All right, how about the next one? Number 1, is it a ring? Yes, it is. Number 2, is it fully conjugated and flat? It is. Let me draw the sigma framework. All right, so we've got a pi bond, so I'm going to represent it with the p orbitals. We have another pi bond here, represent it with the p orbitals. And remember, the nitrogen at the top has a lone pair, just like we saw up here with the amide. The nitrogen with a lone pair, now it does have a hydrogen, we just didn't draw it. But that nitrogen has 3 bonds and a lone pair. That lone pair is just part of its structure, and it looks sp3, but because it's allylic, it can participate in resonance, and it will. So therefore, there is full conjugation around the ring. Now you might ask yourself, but what about the lone pair on the other nitrogen? Doesn't the other nitrogen have a lone pair? Well, it does, right? Look at the black pi electrons. These are the black pi electrons. This nitrogen has a lone pair, but it is not in the p orbital. The pi electrons for the double bond are in the p orbital, the unhybridized p orbitals. You can't have another orbital in the same space with the lone pair in it, because the one that's in the y direction, the one that's, that you're using to do all of the conjugation, is taken up. That lone pair is therefore in the orthogonal plane. So there's your lone pair on that nitrogen. So the nitrogen at the top, notice that the nitrogen at the top has a lone pair, but that nitrogen is not part of a double bond. So it can use its p orbital to be in sync in conjugation with the pi system. The nitrogen at the bottom has a lone pair, but it also is part of a double bond, so it has to put the lone pair orthogonal. Think of it very similarly to that alene system in conjugation that we showed, right? The carbon in the middle is already part of a pi bond. So to do another pi bond, it has to use the other plane. So the nitrogen, you've got to pay strict attention. You can't just go start counting all lone pairs and whatever. You have to consider what can play in the p orbital alignment conjugation game and which ones are orthogonal, because that nitrogen does have a lone pair, but it also has a pi bond, and it's the pi bond that is more important in conjugation, right? It doesn't need that lone pair. And in fact, that lone pair is out of sync. It's orthogonal, and it's not in the conjugation game. So, counting them up, we had 2, 4, 6 electrons, because we passed the first 2. We have 6 pi electrons, which fits the 4n plus 2 rule. This is aromatic. So all of these rings that we just did are all aromatic, and they all have added stability because of this aromaticity. Now this last case I'm showing you, and this is a tough one. This is not something I would give you on an exam. And the reason being is that you pretty much need a modeling kit to recognize that this one is non-aromatic. So in the first case, you'd ask, is it a ring? And the answer would be yes. So it passes the first test. Where it fails is in the second one. It looks on first glance that it's fully conjugated and flat. But it's actually not fully conjugated and flat. Take a look at the structure. When I make a model of this, we've gotten to the point now where the ring is so big that it bends. And what happens is, in the bend, is that if it's not flat, then the orbitals can't overlap and align with one another. So when there's bending, the orbitals go out of alignment and can't overlap. Therefore, there's no conjugation. So when you have this bending in the ring, you end up losing that full conjugation. The orbitals, even though they're all sp2 carbons with p orbitals, they're just not aligned because of the comfortable nature of how this ring wants to be. And so this is not an aromatic system. This is just I just wanted to show you an example where number 2 can fail, non-aromatic, because it fails the full conjugation flat rule. I leave you with some added practice to understand the full capacity for aromaticity. In the first question, I'm asking you which one is more acidic. So I want you to do what you do. Consider the proton and do your acid-base chemistry and try and figure out which one and why, which molecule and why is most acidic. I then want you to look at the nitrogen, right? Because these are amines. These are amines. Which amine is more basic? Which one wants to go out and grab an H+? Why? Explain your answer. Then at the bottom here, I want you to use the IUPAC or common name rules to practice your ortho, meta, para naming. You can use 1, 2, 1, 3, 1, 4, but I also want you to attribute ortho, para, meta to them and just practice a little bit of naming. And then in number 4, I want you to classify each of the compounds given as either aromatic, anti-aromatic, or non-aromatic. So I want you to practice using Huckle's rules.